All right, guys, so this is week 7, and we're going to get into the review for the unit test coming up. So let's just jump right in. So the first part is just kind of definitional ideas. So I'm just going to type the number and the answer over here. If I can get it, there we go. So the first question says the attractive force that exists between all objects with mass is the force of gravity. That's the word that you're looking for there. Most of the time, the mass that is attracting things is the Earth, though. Number 2, a force exerted by a segment of rope or string on an object is called the tension of the object. 3, the vector sum of 2 or more forces acting on an object, that is the net force. You combine all the forces together, you get net force. 4, F equals ma is known as second law, Newton's second law. 5, net force of 0 occurs when the blank is also 0. That would be when the acceleration is 0. Another case with this, to describe this would be that the forces are balanced, and then because of that, there is no acceleration. An object at rest remains at rest is part of Newton's first law. 7, whenever one object exerts a force on a second object exerts an equal force in the opposite direction on the first. That is known as Newton's third law. That's an action-reaction pair. Number 8. Tendency of an object to resist a change in its motion. That's inertia. Mass. The amount of mass is the amount of inertia for an object. Perpendicular contact force exerted by a surface to prevent penetration. That's the normal force. 10. In a blank, dot represents an object and arrows represent forces. That's a free body diagram. 11. The cause of forces are known as agents. Those are the items or the objects or things that are causing the forces to occur. And finally, 12 is a contact force that resists motion. That's friction. So friction is the thing that holds things in place or slows them down as they are moving. So just definitional ideas. Hopefully those are all straight in your head. So in this first example, we have 2 books. Book 1 is at rest on top of book 2, and book 2 is at rest on top of a table. And we're trying to find the magnitude and direction of each of those forces acting here listed. So force of book 1 on 2, that's like asking how much is book 1 pushing down on book 2. The next one is the force of 2 on 1, so book 2 pushing up on 1. So we can kind of see the directions already, so I'll say that's down and that's up. And if you notice, if you look at the wording of that, that's an action-reaction pair. So 1 is pushing down on 2, 2 is pushing back with an equal and opposite amount on 1. So that's how that's going to work. And then similarly in the last 2 rows in the column, it's another action-reaction pair, but this time it's between the book pushing down on the table and then the table pushing back up on the book. So again, we can list those directions already here without having to do any sort of calculating or work. So the way that I would look at it is in a free body diagram. So the first one here is for book 1, this red dot. So the force of gravity for the Earth pulling down on book 1 is happening. If we just focus on book 1, it's going down. The force of book 2 is pushing back up on the book 1, and that's kind of a normal force. And if you look at those, like we said, book 1 is not accelerating, so the net force is 0, the forces are balanced, and they cancel each other out. So it already tells you actually the weight or the force of gravity acting on book 1, it's 40, so this is just going to be 40 for the magnitude, so 40 newtons. So that's the force of gravity, that's what's pulling down. In order to make it so that it doesn't move, then the 2 on 1 has to be going up with that amount. So that action-reaction pair between 1 and 2 is equal to 40 in both. Then I did a free body diagram for the second book, which is the green dot here. And we have 2 things trying to act downward on book 2. We have its own weight or gravity, and we also have book 1 pushing down on book 2. The table is what's underneath the book, and that's pushing up. And that's canceling out both of those forces down. So if you look at them, it already tells you the weight of 2. So that's 50. And we already figured out in the last part that 40 was the force of 1 on 2, pushing down. So we have 40 and 50 going down. So together there is 90 total of book 2 pushing on the table. And we have 90 from the table pushing up, or the normal force on the table. So that is the correct idea. Okay, so that's those, just kind of looking at a situation and talking about forces and action-reaction pair concepts. All right, so the next one here says, number 1, what is the tension in a rope that is being used to accelerate a 200 kilogram crate upward at 1.2 meters per second squared? So again, you need to draw a picture, which I did over here. So looking at the first case, the net force, the net acceleration is going up. We have gravity pulling down on the crate, and then the rope is pulling up. And in order for it to accelerate upward, or the net force has to go upward, so the bigger force is the tension going up. So I'm just going to kind of write out my sigma F, or net force equation. So my net force is equal to the tension, which is positive. So if you want a little plus sign there, that's okay. You don't have to put a plus sign because it's implied. You do need a negative sign for the force of gravity, though, because it's directed downward, and we want to make sure that we have the correct direction on these. And that would equal the mass times the acceleration. So really it's just plugging in to these values. I'm going to thin up the line a little bit. So if I do that, Ft is what I'm solving for. The force of gravity would be the mass times the acceleration. So it would be 200 times 9.8. 200 times 9.8 is 1,960. So 1960 is going to go in here, and make sure you remember that negative sign. And that's equal to the mass, which is 200, times the acceleration, which is 1.2. If we do this math, 200 times 1.2, that's 240. And then you're going to move the 1960 to the other side and add it. So when you do that, you add 240 to 1960, and you end up with 2,200 for the tension. So 2,200 newtons is the tension that's required to make it accelerate upward at that acceleration. The second problem is almost identical to the first, except this time you're accelerating it downward. So if you look and draw a free body diagram again, you got your force and your acceleration. This time they're directed downward. So the gravity force doesn't change. That's still 1960. It didn't change because it's the same mass. But the tension is what adjusts. So the tension got smaller. And because of that, there was a bigger force pulling down than pulling up. So that's why it accelerates downward. So basically the same equation here. Let me try to do this real quick. There we go. So I'm just going to take a picture of that because it's the same exact. Let me move it back over here and shrink it a little bit. But the difference is when you put in the numbers, it doesn't work out exactly the same. So the tension is still Ft. Gravity is still a negative 1960. Mass is still 200. The only thing that changed is that acceleration is now negative. So it would be a negative 240, or negative 1.2. Okay, so if I kind of just finish this up, Ft would equal negative 240, because that's 200 times negative 1.2 plus 1960. So the difference in those two for the tension is going to be equal to 1720. So 1,720 newtons is the tension in that rope. So again, that makes sense. The tension going up is smaller than the gravity going down. So the net force is down. It's going to accelerate downward. Okay. Next one here is talking about a horse is pulling on a plow with a rope, and that rope is at an angle. And we're going to try to figure out the various ideas that go along with the situation, the net force, the net acceleration, all the other forces that are associated with this. So again, you start with a free body diagram. So if that's my plow, the forces acting. So I'm going to label this tension. So there's tension in the rope that the horse is pulling on. And we know the amount and the angle, so that is useful. 50 kilograms, that's the mass of the plow, so we'll use that later. It says if there's a coefficient of 0.67, that's the coefficient of friction, so that's U. And now we just have to kind of finish up with the free body diagram. So we did our force going in, our weight or force of gravity going down, like normal. So again, because the rope is at an angle here, or some angle, it means that there's going to be components. So you're going to have to figure out the components, like how much is the tension pulling to the right, how much is it pulling up, and then we also are going to have a force going up from the normal force, so that's going to be Fn. But this normal force is not the same size as the force of gravity. If you notice, it's smaller, so this green arrow is bigger than this blue arrow, because both of these blue arrows, the tension in the y and the tension in the x, the tension in the y and the normal force are both pulling up, so gravity is going to cancel that out. The other thing that we're going to have is we're going to have friction, and that's going to go the opposite way to our pulling force going to the right from our tension. So we just have to go through and complete the chart. That's my suggestion for you guys, is to go through, complete a chart, and then fill in the chart and solve for what's going on. So I like doing the plus minus zeros part. So looking at it, gravity does not go left or right, so that's 0. Gravity is going in the negative y direction because it's down. Tension is going both right and up, so those are 2 positive values for that. Normal force is only going up, so it's 0 and positive. Friction is negative because it's going in the x and it's going left, and in the y it's 0. The net force we're not sure about, so I'm going to leave this blank. Friction is never going to be great. Like if friction is the same, it will go to 0, but friction is never going to be bigger to make it start moving to the left here. So I would predict this positive. I'll leave it alone. But we definitely know that the plow is not getting raised off the ground or falling through the ground, so there's no acceleration there, so that's going to be 0. So we just have to do the math with these different values. So we'll start with gravity, because that's a really basic one, and you guys should be okay with it. So force gravity is equal to mg. So mass is 50, g is 9.8. 50 times 9.8 is 490 newtons. So 490, that's an n, sorry, is going to go in this side of the chart over there for Fg. Again, that's just the mass times the gravity. You guys, I think, are mostly pretty good with that by now. For the next one that we're going to worry about, that's going to be the tension. So let's try to find the tension in each direction. So tension in the x and tension in the y. Similar work for both of them. It's the amount of force, which is going to be 500, times the trig function, which is cosine for x in this case, and then the angle. So it's always the cosine of an angle. So 500 cosine of 25 for the x, and if you put that in your calculator, you should get, I got a value of 453. And if you round it to 453, that's fine. I think I went out a couple more digits, so I'll just be consistent so that I get the same numbers again. So 453.15. Then in the y, really similar work, 500 sine of 25 degrees. These are the degrees. Remember, it's always the cosine or sine of an angle. So the pull in the y, I got 211.3. Again, that would be newtons. There we go for there. And then we don't really have enough to get the force of friction yet, or the net force yet, but we do have everything in this y column except for this one missing box. So if I put the green square over there, that's the one we're going to solve for. And what we're going to do is we're going to use the y direction kind of and add these up. So again, the y direction should balance, so whatever this 211.3 plus whatever this number is should cancel out the 490 going down. So this value here is a 278.7. So 278.7 newtons is what the normal force is. And this problem didn't actually ask for that, but you have to do it in order to get to finding the net force and finding the acceleration. So now we do have enough information to work to solve for the force of friction. So we're trying to solve for that force there. So the force of friction is equal to U times Fn. So the coefficient was the 0.67 number that was given in the problem. And the normal force we just got was 278.8. Or 278.7, excuse me. So when you multiply those out, you'll get a value for the friction of 186.7. So 186.7. And I'm going to take that and put it in this box here. So 186.7, that is my friction. Now we're just left with kind of solving for the net force. And we can do that just going down the column. So if we take positive 453.15 and subtract off or add negative 186.7, you should get a value of, let me see, I didn't write that number down, so let me go ahead and do that. So try it again, 453.15 minus 186.7. I got 266.45. Okay, so that is the net force, and then we're going to use that to solve for the net acceleration. That's newtons. All forces are measured in newtons, so that's part A. And then we're going to use that value in part B. So in part B over here, we're going to do Newton's second law, which is the net force is equal to ma. So we have the 266 value, 0.45, and we're going to divide that by the mass of the object. So the mass of the object was 50 to be able to solve for A, which is what we want. So we're going to divide both sides by 50. And if you do that, you will get an acceleration of 5.3 meters per second squared. And that acceleration is also going to go in the same direction as the net force, which is to the right. So that is the answer for it. All right, so the next one is just an Atwood problem. It's a pretty basic Atwood machine problem. So again, you approach these by selecting a system. So we're going to circle the whole thing because we want to take this whole system and talk about how it accelerates. And we need to pick a direction for which way it's going to move. So the heavier side over here is 24 and the lighter side is 12. So I think the way it's going to rotate is that way, or how I would describe it is counterclockwise. I'm just going to call this one B and this one C. So when we refer to blocks, it's easier to label things. So what we're going to do, we're going to draw our forces that are acting external to our system. So the first force acting external to the force system is the force of gravity on B. So this force of gravity pulling down there, and then the other force of gravity C, is also pulling on the other side of the pulley. Now, you have to line up these arrows with the direction of the acceleration of the system. So B is going to be positive because that's the heavy side, and C is going to be negative because that's the lighter side. So really, after that, it's kind of just a normal net force kind of problem. So the sum of the forces, or the net force, is equal to, and then you just really put a plus sign between those two forces. So it's the force of gravity on B plus, and we have the negative force gravity C. And whenever you add up all your forces, you can always use Newton's second law. So when you add up these forces, you get ma. Now, the mass is the mass of your system, and we circled the whole thing, so this would be B and C together. So we got both of those masses put together. So now it's just going through and filling in and finding the numbers. Again, we're going to use FG is equal to mg for the gravity or weight calculation. So I'm just going to write out the numbers here. So this would be 24 times 9.8. And then we have negative, and that's going to be 12 times 9.8. And then when you add the two masses together, 24 and 12 is 36. And then A. So A is what we're going to solve for in this part of the calculation. So if I write this out, it's 235.2 for the weight or gravity of B. C is half the mass, so it's going to be half the weight as well. So that's 117.6. And that equals 36A. If you do the math here, 36A just comes down, but if you add 253.2 plus a negative 117.6, you get a positive 117.6 because it's half. So you get the other half remaining, and then you divide through by the 36 on both sides to get the acceleration value. And you should get an acceleration of 3.27 meters per second squared. And that is the direction that we picked going, whatever our positive direction was. So that is the answer to part A, the acceleration of this Atwood machine. The next part is to solve for the tension. To do that, you just have to isolate for one block. So I usually pick the heavier block and solve for it. So if this dot represents the forces acting on the heavy block, we have the gravity force, which is going down. So it's gravity on B. And the only thing going up against it is the tension. If we think about this, again, we decide which way it's going to move based on the acceleration of the system. So I had down as positive, so I'm just reminding myself of that with that little symbol over there. So that's going to make the gravity of B positive. It's going to make the tension negative. Gravity of B should be bigger than the tension. And we're going to do the same kind of work here and solve. So I'm just going to write it out here. So the sum of the forces on B this time is equal to the gravity of B, which is positive, plus the negative tension in that rope. And you could have solved it using the other block. It makes no difference. Block C could have done the exact same kind of work. And then that's equal to the mass times the acceleration, Newton's second law again, but this time it is the B block only, because it is just the B block in this picture that I was drawing on. So that's essentially what we're doing. We already know some of these numbers. So 235.2 is the gravity of B. Tension is what we're looking for, so negative F tension. And then it's going to be the mass, which is 24, and our acceleration that we just found in part A, which was 3.27. Basically, you trade these two terms and solve for Ft. And when I did that, I got 156.72, so 156.72. And that is the answer to the tension. If you wanted to check it, you could do this tension pulling up on this side minus the gravity going down, so it'd be like the 156.72 minus the 117.6, and then set it equal to 12A and solve for A, and you'll get the same acceleration. So it does work out. I did check it. So the next one we got is our incline problem. So incline's a little tricky. It's trying to make sure that you do the steps again. I would suggest looking over them and the ideas and trying to make sure you're good with them. So we know it says the acceleration of the block on the diagram is 5 meters per second squared. So that's the net acceleration. And we want to know what's the coefficient of kinetic friction. So this problem is just only asking for U. So we're trying to find U, UK if you want to be specific. But we're gonna draw the forces acting on our block here. So if this red dot represents the block, I would say we have gravity pulling down. We also know the angle here is 60, that they gave us that. Perpendicular surface is the normal force. So that's the blue arrow going that way. And then finally we have friction, which is going up the ramp and trying to stop it from moving or slow it down as it moves, which is what's happening here. So the force of friction. So what we do again is we tilt our axes so that our x-axis is going down the ramp, our y-axis is perpendicular to the ramp, and then we line up our forces with that. So gravity is the only one that is tricky. So gravity has components in both the y direction. So part of gravity pulls kind of in, that's the y gravity there. And then we have the x gravity, which is pulling down the ramp. So we have both of those. So this is one of the things that we're going to do just to make sure we do our positives and negatives right, and zeros. So gravity in the x is pulling down the ramp parallel to the ramp, so that's positive. Gravity in the y is pulling into the ramp, so that's the negative y. The normal force is going perpendicular ramp, so it's not going parallel, which is the horizontal part. It is perpendicular and it's positive because it's up off the ramp. Finally, friction is going up the ramp parallel, so that's negative in the x, and it would be 0 in the y. Again, the box isn't going to fall into the ramp or get thrown off of it, and it accelerates in the positive direction because it accelerates down the ramp. So there is the setup with our positive, negative, zeros. We need to fill in numbers. So really this comes down to finding the gravity in the x and the gravity in the y. So gravity x, gravity y. Again, it's very similar kind of work here. This is a little bit different than the normal one. So we did the problem with the horse pulling the plow earlier. This one, this way you calculate x and y is slightly different. So again, make sure you pay attention. So the gravity in the x would be the force of gravity times the sine of the angle of the ramp. So first off, force gravity again, just mg. So I'm just going to write out the values here. So it's going to be 20 was the mass of this thing. Gravity is 9.8. So that's m and g. And then we're going to have our trig function. So because it's the incline, x goes with sine. So this would be sine of 60 degrees. And then for the y, it'd be 20 times 9.8 times the cosine of 60 degrees. If you go ahead and put those in your calculator, or if you're checking your work, for the sine one, for the x, that's 169.7. So that's going to go on the x here. And then in the y, it's going to be 98. So we fill in the gravity in the x and y. We can also do the net force because we can just use F net. Is equal to ma, which is Newton's second law. So it's going to be the mass. Again, the mass is 20. And the acceleration is 5. 20 times 5 is 100. So now if you look at our chart, it doesn't look so empty anymore. We're missing the friction in the x column and the normal force in the y. So we just have to kind of make these work. So 169.7 plus a negative number equals 100. So it's going to be the 69.7. And then negative 98 plus some number gets me 0. So that's going to be a positive 98. So I have found, I don't know what that dot's doing. I have found the two missing boxes, and those are actually the two boxes that we need to solve our problem, which is to solve for the coefficient of friction. So the coefficient of friction is in the friction equation, so FF equals UFN. So it's going to be 69.7. You don't have to worry about the negative when you're looking for a coefficient because there's no direction negative is based on this scenario. And then 98 for the normal force. So you divide through by 98 on both sides. And you got to solve for u. And when you do that, you get the coefficient of friction is something like 0.711. So this is a pretty large coefficient in terms of just coefficient. So there's a lot of friction on this ramp for some reason, or there's a lot of friction between the block and the ramp. So the last one we have here is dealing with a tractor. So it says a tractor is being used to pull two large logs across a field. A chain connects the logs to each other. The front log, so I'll draw like the front log and the back log. I'm going to say B for back. And F for front. They're connected by a chain, and then there's also a chain that pulls, and that's attached to the tractor. So I'm just going to label this force a tractor, because that's what's pulling the whole system. And then between the back and the front logs, we have FT for tension here on this one. So we'll just call that one tension. So they give us lots of information. They give us masses of the front and back log. They also tell us the coefficient of friction. They tell us the chain connecting, the force of the tractor, basically. And we want to figure out what's the acceleration and the tension here. So we're looking for this tension, and then we're looking for what is the acceleration of this whole system. So this approach is going to be similar to, if you remember, we did a problem with multiple blocks, where we had like 3 blocks and there was a force pushing, if you remember that in the example problems. So it's similar to that. It just has ropes instead of normal forces here, but you could do similar work if you had normal force. It doesn't matter. It's just a tension instead of a normal force. Just to discuss kind of the forces acting, we have several forces acting in this system, but let's just draw it as a simpler system. So we're going to circle that and call that our system. That makes tension internal, which means I can't solve for it, but I can solve for the acceleration. So this dot represents both logs together. We got the tractor pulling to the right. We got gravity pulling down. There's going to be a normal force going up. And there's going to be friction resisting the motion. So this is the force of friction on everything. So this is on both logs, so it's B and F together. These would all be BF labels, so it's the normal force on B and F, so both logs again, and the gravity of both logs. So doing this, what I'm going to say is, again, the normal force and the gravity are going to balance out. That happens a lot of times. These set of logs isn't going to fly off or fall through the ground, so those cancel out or balance. The tractor is pulling to the right, so that one's going to be positive. Friction is going to the left, so that's going to be negative. And when you add those forces together, that's essentially what you need to get for the net force. So it's the force of the tractor, which is positive, and then a negative force of friction. I'm just going to leave it as FF for force of friction. We're going to have to use some values and solve for some things here to get to the force of friction, but that's okay. And we can set that equal to M times A. We are looking for A. That's what we're solving for. So again, it tells us some things. So it told us the tractor was pulling at 1850. The force of friction, we're going to have to do the friction equation, which is UFN. We already said that the normal force is the same as the gravity, so we can write this as U times mg. So that's what I'm going to plug in to get this friction. So I'm just going to start plugging in numbers. So it's a negative, and then the coefficient was 0.45. Sorry, I had to find that in the problem, 0.45. The mass of the logs, we have 180 and 220, so that's going to be 400. And then we have 9.8 for the acceleration due to gravity g. And that's equal to the mass. So again, the mass would be 180 plus 220, so that's going to be 400. And then we're solving for A. So there's where we're at. And we're just going to plug it into the calculator and get some values to calculate that. So 1850 is this value, just to check, but because I want to make sure I'm saying the right thing. So 400 times 9.8 times 0.45 is 1764. So yeah, I did have that right. So it's going to be this whole thing is 1,764. And the difference between those two numbers is equal to 400. So if I subtract 1850 minus the 1764 number, you get 86. So we got 86 equals 400A. You divide both sides by the 400. And we get a pretty small acceleration, but they're pretty heavy logs. And you're going through some mucky ground. So we're solving for A here. And you should get an acceleration of 0.215 meters per second squared. So that is the acceleration. Now we need to find the tension in the log. So what we need to do is we need to break these up, the system up into individual pieces. You can really use either one. So if we did the back log or the front log, it doesn't really matter. I usually try to think about which is going to be easiest to work with. So this one has the force of the tractor pulling, which we know, so we got that number. It also has gravity and normal force, but again, they cancel out. But you'd need to find them. You have the rope or the tension between the two back and front logs, and it also has friction. So it has three, and this is for the front, it has three different forces acting on it. I think that's more difficult than B, or the backlog. So if you do the backlog, you got gravity, you got normal force. They're going to cancel again, but we're going to need to find that number because we need it to get the friction. We have just the tension, which is one thing that we're looking for, so that's good. And then you have the friction on B. So I think this, if you're looking at just counting the pure number of forces, this has one less force, so that's the one I'm going to use. So kind of doing the same type of work. You're starting with the sum of the forces on, this time, the backlog is equal to the tension, which is positive, which is what we're solving for, plus a negative force friction, just on the backlog, is equal to mass times acceleration. And this mass is the mass of our system, which is going to be B. So that is what we're going to use to try to solve for this last bit of information. Ft stays the same. We're going to do the same type of work here with, well, I wrote normal force here. This is the normal force is just equal to mg. And then to get the force of friction, you get UFN. Oh, yeah, I did that right. So, yeah, I started with force friction here. I was just confused. So this is the force of friction, and that would be right. Never mind. So anyway, we're still going to use this UMG idea to get the force of friction here. So the U value is 0.45. The mass is less, so this is just the backlog. So if you take a look, the backlog is 220. 9.8 is the acceleration due to gravity, so that's that side. And then we have the 220 times the 0.215 acceleration. So, and there's a negative here. So you're going to bring this over to this side, it becomes positive, and you add those two values together. The tension turns out to be 1,117.5 newtons. And again, if you're not confident in that answer, go ahead and check it in this one. So you can put the tension is this 1,017.5. And then, you know, the tractor pull is 1850, and you could solve for this force of friction on the front log, but you'd have to do this kind of work with just the 180 number instead of the 220, but it does work out. It gets you the same thing, so that's a good feeling. So that is all of the force review. So hopefully that was helpful, and if you have any questions, just reach out, if you will.